Greetings. Welcome to. Oh, look at that. That beard. I trimmed my beard. Uh, so, on the teaser I did the other day, I said we're going to do some exam reviews, and that is my intent for statistics. Give you a sample of what I plan to do. It's either going to be done here in front of a chalkboard, or I'll do it in a tighter format, based, just like the other statistics videos I have up on the Tutor Wizard, where I keep them fairly compact. But today I want to ramble on because I got all this nervous mental energy, and I want to get some stuff out there, typical of how I like to talk about statistics. I'm not going to go all hardcore mathematical on you. I'm going to do a little math like this, but we're going to talk about how analysis of variance is handled in general. Usually, one thing that happens, I'm not seeing it so much this semester, at least in the with the students I've been working with and talking about how their classes are going. But oftentimes, what happens is, as the end of the semester catches up to everybody, you find out that you're behind time, and the last topic or two gets just sort of, okay, well, we'll learn more about it next semester, that kind of thing. So analysis of variance, then, at least one way analysis of variance, quite often falls into the category of, oh, we're running out of time, so just memorize the hell out of this, and we'll talk about it in the next stats course. But if you've never taken a next stats course, you're out of luck, right? So I'm going to fill in a few blanks. So we're going to do one-way analysis of variance today. We're not going to work with raw data, but we're going to work with some descriptive statistics and build things from there. And I don't have any cheat sheet notes in front of me, so we're doing this all from memory. That should be safe, although there may be a few artifacts floating around in there, but we'll have some yucks along the way, perhaps. Okay, so why are we doing analysis of variance? Well, with analysis of one-way analysis of variance is essentially a glorified t-test. So with pooled standard deviations, as you'll see in one of the formulas coming up here. So when you have three or more samples well, not categories, that would be a specific language for chi-square, but when you have three or more treatments, you have to have a way to analyze them. And if you could say, well, why don't we just do repeated two-sample tests? Well, the problem is you incur an error when you do that, which can be addressed with the Bonferroni technique of, scaling the level of significance downwards as the number of pairwise comparisons goes up. But that's a perfectly valid technique. But sometimes you call these kind of tests here an omnibus test because it gets it all in one shot. So yeah, that's the basic idea. And what you're trying to do is, I keep wanting to use this chalk for some reason. We'll get around to that in a minute, but I've got to talk with my hands. And I'm not even Italian, although maybe Lorenzo's rubbing off. I don't know.
I bless you as an honorary Italian.
I'm an honorary Italian. Okay. So you got to watch out for those honoraries. They cause trouble. The peanut gallery over here is beaking off again. So the idea is with analysis of variance is you're going to have various treatment groups, right? Samples. And they're all going to have a mean value. And so if you've got, say, 5 means, guess what? There's a variance between each one of these means. Now, if you strip away the treatment structure and you just take all the observations, put them together, so now you've got this huge pool of observations, well, there's a mean value to that. And of course, there's a variance to that. So a significant result occurs when the variance due to the structure imposed by the treatments is much larger than the variance imposed, well, when you strip away the structure and you just take all the observations. So if you're looking at treatment sum of squares and then you modify that down to mean squares, all of this is going on the board. I'm just giving you some peremptory rabble. Rabble? Rambling? That'll work. Rabble. Well, whatever. The point is, if the mean squares of the treatments is, say, 20, and the mean squares of the errors, which is how we talk about observations, is 4, then 20 divided by 4 gives you your test statistic of 5. And then with most degrees of freedom, that's going to be a statistically significant result because the variability due to treatments is 5 times larger than the variability when you strip away the treatments. So that means the treatment structure is significant. And that's the idea here. Okay, so let's talk about the base formulas, which in most cases nobody does this by hand anymore. You could if you wanted to, just for giggles. It's very instructive. But we need sum of squares. So when I put the table structure up here, I'm going to have column labeled SS for sum of squares. And that's how we're going to measure the raw variability. So we need sum of squares for the treatments. And so that's going to be SS subscript TR. So this is going to be the sum of each group's average minus double bar, which is the grand mean, the mean of everything. Of course, we got to square that, and then we multiply it by n. And that's where you're going to get your... Oh, wait a minute. No, that's not right. Hang on. This is what I meant about, I'm doing this from memory. So is this going to be n? Yeah, this is n. Okay, so n sub I. And then we have sum of the squares due to the errors, or the observations, which is going to be n minus 1, ni minus 1, times si squared. So this is right out of the pooled standard deviation formula for the two-sample t-test. This is what I said earlier about this being a glorified t-test. So if you have the raw data, you can get the average for each group, and you can get the average for all the observations. And the difference between the two, of course, you're going to square away the negative, multiply by n, and away you go. This will give you a value. And here, this is just n minus 1 and the variance. And that's not supposed to be a 1, that's supposed to be an I. Okay, so those are the base formulas. We don't use that anymore, but I mean, if you wanted to do it by hand, you could. But this is what's hiding under the hood, the mechanics of the analysis of variance technique. Okay, let's get rid of this. Now, yes, there's degrees of freedom involved with this. We'll get to that towards the end. The hypothesis, I've already suggested how that structures. The null, of course, means there's no significant difference amongst all the treatments. And this is always the case, that H null means there's nothing going on. So we could label that as mu sub 1 is equal to mu sub 2 is equal to however mean values there are. Whatever. Now, we could also say that all the means are the same. You could essentially do it with language if you want, and some instructors do, some do the notation thing. And the alternative hypothesis, so if we reject this, we have to have something, and what we have is at least one mean, so I'm going to use mu sub I for that, so at least one mean differs from the others. How's the clacking on the chalkboard doing over there? Is that annoying, do you think?
Nope.
Okay, cool. All right.
It microaggresses me.
Okay, it's microaggressions? No, not enough yet, but let me get there. Where typically for levels of significance, we're going to use 5%, but remember, you can set that to whatever you want it to be. Okay, let's get on to the most important thing, which is the structure of the table. Now, I know with the formula sheets that I'm familiar with, this is abbreviated into the test statistic F is equal to some long, messy, hard to interpret unless you're a math nerd layout. So we're going to do this differently today. I'm going to make a table here and I'm going to annotate it as to what goes where and how to do computations with the table. It's dead simple. This is nothing hard about this. Don't talk yourself out of easy marks on the exam. You know, if I had my druthers, which is a word, by the way, you can look that up. I would much rather do analysis of variance any day of the week than a whole bunch of two-sample t-tests. Ugh. It's my nemesis. Okay, so our typical layout is treatments. Is in the first row. Oh, I'm going to run out of room here. I'm going to be careful about this. Okay, this isn't an 8-foot board. Okay, try it again now. So we're going to have treatments over here. I was going to write treats, but there's a bunch of cats floating around, so they'll come by going, tuna? Hello, tuna? Treatments. This is sometimes called groups, by the way, unfortunately. Then we have errors. So this groups, by the way, is oftentimes notated with between groups. And this is within groups. Again, this is older notation, but oftentimes shows up. And then we need totals. Okay, let's make a table. Okay, I'll probably have to erase that. So we're going to start off with the sums of squares. You paying attention to this? What the hell is your name over there? Adrian, that's it. Adrian's taken it on himself to tutor a little bit of statistics as well, so I know he'll have to encounter this. So this is for his benefit as well. So this is SS. Okay, now. And then we need degrees of freedom, which will be DF. Let's do it this way.
You do it. What I said. Like, no.
Degrees of freedom, also known as DF. Okay, I'm going to have to erase that because of reasons. Let's get this out of here. There we go. Oh, there you are. I knew you were floating around here. Come up here, sexy cat. Oh, this is Milo. Yes, and Milo got a bit of a cross eye, but he's a wonderful kitty. Yes, you are. Who's a good boy? Who's a good boy? Who's a good boy? Whoop. Okay, so can I do stats with the cat? Nope, the cat don't want to be anything around there. Okay, you get out of here. Shoot. All right, you rub me. All right, now we got to have a column for this. Then we need MS, mean squares. And then over here, we need our test statistic F. Okay, good enough. Test stat. So that's the general layout. I will say one thing, though. Sometimes this column and this column are flipped around. Microsoft Excel, for instance, if you use the analysis tool pack, produces degrees of freedom and then sum of squares. I think SPSS does too, but this makes much more sense to do it this way. Now,
No, I want it now. Can I have the food now?
Sorry, the cat's being ridiculous.
are you, it sounds like there's cat loving going on over there.
Yeah, he wants his food. He's coming back to you. He's coming back to you.
Hey, pussycat. Oh, I'm getting rubs. Oh, you're such a wonderful God. This cat, by the way, doesn't officially live here, but comes by, wow, I'm getting aggressively rubbed.
Yeah.
Wow.
Cold outside. I'm not going back to that lady's house.
Oh, come on. Come on.
Point out that he doesn't live here.
He's unfixed either as well, so he still has his trouble puffs, as my wife would say. Also, you know, you keep that up, you're going to have to come up here and do some math. Okay, so here's our general layout of the table. Let's put some notation on the table so we can understand what goes where. So remember, sums of squares is how we quantify the variability. So sum of squares for samples then quantifies the variability between the sample mean values. And notation for this is typically SSTR, but it could be SSG. Either sum of squares of groups or sum of squares treatments. So these will be given values, or you'll be able to reverse engineer something to figure them out. Errors, this one here is SSE typically, but sometimes SSW for within groups. Here we have SS totals. Okay, so as you can see, we add vertically. Or subtract if you want to find an intermediate number. Maybe we'll do one of those at the end or not. We'll see. So the thing is with, in more, usually second semester statistics, we can use this, the cat's back. Look at it, if you're gonna, okay, come here. Come on up here, you big guy. Come on, big dude. All right. Hi. So the point I'm getting at is, that in more advanced classes with analysis of variance, we can figure things out using sum of squares of totals as well. Here it's just sort of like a bookkeeping value. Isn't that right? Yes. So, you know, I can't write on the board with you like this. Do you like my friend? His real name is Milo, but around here he's also known as Clancy. And hi, how are you? Oh, just rub some blood. Oh, we're camera shy. Okay, Milo, you got to go do something over here. Woo! There we go. Okay, losing my microphone too. Okay, carrying on. What are the degrees of freedom? Degrees of freedom is typically noted as k minus 1. But what is k? Well, k, I don't want to step on kitten, k is the number of treatments, okay? So we'll go number of treats minus 1. So if you got 5 samples, degrees of freedom are 4. Arithmetic. What about this one? This is big N minus 1. What is big N? Well, big N is the total number of observations. So again, if I've got 5 treatments, and each treatment has 15 observations, then big N is 75. 5 times 15. And then when we subtract, why did I put 1 on there? That's wrong. It's big N minus K. There we go. So in the case of what I'm talking about right now, 75 observations, 5 groups, that means I'd write a 70 here. The N minus 1 is again for bookkeeping. That's down here at the bottom. And again, that's about really the only reason it's there is for bookkeeping or working something backwards. Okay, what are you doing, kitten? Okay, Adrian, you may want to come and get Cat over here.
What's he doing?
I don't know, but it's got suspicious looking cat behaviors going on over here.
Yeah, he's trying to hump everything.
Oh, he still has his trouble puffs. Okay. Don't be trying to screw the math books now.
Are you trying to scooch everything?
There we go. Say bye. There we go.
Know it. You got 11 out of 12 because you made mistakes. You can't add, but neither can I. But
I got 11 out of 12.
no, I did. I'm just yelling into the microphone. I'm yelling into your chest.
You know, I was going to say something smart alecky about that, but I think I'll let that one go for now. We'll see what happens. Okay, so this is the layout for the degrees of freedom column. Capiche? Capiche. Did I say that? That's Italian, I think. Okay. What are this mean squares business I'm talking about now? So if I want to know the contribution of variability that each treatment contributes to the final test statistic, I take the sum of the squares of the treatments and I divide out the degrees of freedom. So here this would have been, let's say this was 500, and we got 4 degrees of freedom here. Well, 500 divided by 4 is 125, so I can say that the contribution of each, on average, the contribution of each treatment to the total group variability is 125 units of whatever the hell we're talking about. So that basically comes down to this. This is MSTR. And MSTR is simply the sum of the squares of the treatments divided by its degrees of freedom. Easy. The same logic applies to the contribution that each of the observations makes to the total variability when we were talking about the pooled, there's that word again, the pooled variability. So here I'm going to have MSE, mean squares of the errors, which is just the sum of the squares of the errors divided by its degrees of freedom. There we go. So this is what I was talking about earlier. So I used the example that if this was 20 and this was 4, then the variability associated with imposing a structure called treatments onto our collection of samples produces variability that's 5 times larger than the variability from all the observations without that structure imposed on it. Now, if we think about that from a slightly different aspect, in other words, in the other direction, what does it mean to be not significant? So let's say we failed to reject the null hypothesis. Well, we're saying the variability associated with imposing treatment structure and the variability associated with no structure are roughly the same. So you're going to have a test statistic close to 1, or maybe even less. Maybe the structure or lack of structure makes this bigger than this. The point is, it's not significant because the imposition of treatment structure makes no difference. And hence we fail to reject the null hypothesis. That makes sense at all? I hope so, anyway. Oh, what do we got going on here? Hello, Adrian. We'll be on afterwards. Yes, indeed. Where's Adrian? Ah, that's Cammy. Okay, Adrian's over there. He's playing a video game, which is perfectly fine. I think that's what he's doing. Oh, he's got a cat over there. He's doing something with a cat. Okay, what do we got here for a test statistic? Well, this is this thing divided by this thing. So F, our test statistic, is MSTR divided by MSE. Here we go. That's the structure. And this is all you need to know. If you know how this table goes together, you can figure out all your values. So what am I getting at? If I take this and divide it by this, I get that. If I take this value, divide it by this value, I get that. And then, of course, this divides by this, test statistic. We're done. Okay? So that's the structure of the analysis of variance table. And for 100 level statistics courses, you just need to be able to sort this out. And once you do that, you're good to go. So let's do an example here. I'm going to replace all this with numbers, or I'll leave some numbers out. And then, well, here, let's just start over here. We'll see what we got. I'm just going to make up numbers, so Lord knows what'll happen when I do that. But I've been watching Murderbot a lot. And within Murderbot is another there's an entertainment show called The Rise and Fall of Sanctuary Moon, which is a real rip on a lot of sci-fi stuff. Well, anyway, Murderbot, you don't have to look this up. Great series of books, too. I haven't read them all, but I plan on it. Anyway, boldness is all. So that's what we're gonna live with Murderbot's boldness is all. Okay, there's our table. So a typical question that you're gonna get is some of the numbers will be filled in here, and you need to fill out the rest. So I'm gonna pop some numbers up here. I'm gonna find numbers that I can reasonably do in my head, and we'll figure out what the test statistic happens to be. So let's make this kind of big down here. We'll make this one 3,600, because why not? I think the Babylonians would appreciate that number too. This is 99. This is 4. Ooh, I need to identify what this is too. There's something special going on there. Now we need one more thingy bobber here. Let's make this 600. Okay. So here's a typical example. They'll tell you, well, what's the test statistic? Oh, I don't know. Well, figure it out, dummy. If you've got 2 out of the 3 numbers in a column or a row, you can answer by a little bit of algebra, you can figure out the missing number. For instance, this, obviously, is 3,000. This plus this, well, that's got to be 95. Now, what does this tell me? This tells me that I had 5 treatments, because this is k minus 1, remember? And this is n minus 1, so now I know I have 100 observations, and it doesn't have to be the case, but typically it's the same number of observations per treatment. Doesn't have to be, but for user friendliness it often is on exams. So that means there were 20 observations in each of 5 groups. Now this number divided by this number is 150, and this divided by that's got to be 30 and a little itty bitty bit. So this will be 3. That'll get me to 285. And then I'm going to have, did I say 285? That's right, 15, 150. So this will go once. That leaves me 55 95ths. So 55 95ths is 11 over 19. So 31 and 11 19ths. So if we round this down to 30, and 30 goes into here 5 times, Now this is going to be a little bit less, so this will be about 4.93, give or take. There's our test statistic, 4.93. What does that mean? It means the variability associated with imposing treatment structure on our collection of data is almost 5 times the size of the variability from not having any structure imposed on our observations. And hence, this is quite likely a significant test result. You would have to either have a computer to get the proper p-value, or you would use a table. And I'm not going to do a table example today because it's a pain in the ass to do one by hand here, because you're going to have row values and column values. Just use the software. That's all you got to do. Okay? Now, I gave a hint that this is special. What the heck is this? This is your pooled or combined variability. And oftentimes on exams they ask you, well, what is the pooled standard deviation? If you need pooled standard deviation, you have to take the square root of that number. So it's the square root of 32, 5.6 maybe? Let's call it 5.6. Maybe a bit more. We could figure it out. What is 5.6 squared? Okay, for those of you who are calculator challenged, that's a 6, that's a 33, this is a 0, that's a 8, and this is a 2, so this is a 6, a 3, a 1, 31.36, close enough for the girls I go out with. Bing! Okay, so there's your standard deviation, your pooled standard deviation. Now, one other thing comes to my mind that you need to know for the exam, and that is, how do you answer the question when they say to you, please report the distribution of the test statistic under the null hypothesis? That's usually how they word it, for no other reason than it looks like ultra old school. Yes, it is, because why not? Okay, so you have 2 degrees of freedom you need to report. You need the degrees of freedom associated with the treatments, which remember was 4, and the degrees of freedom associated with the observations, which was 95. So we can say the degrees of freedom on 4 and 95 degrees of, the test statistic on 4 and 95 degrees of freedom is F, which is the probability distribution family, which is 4.93. Yink, there we go. That's how you do it. And that's about all there is to one-way analysis of variance as typically encountered on final exams coming up. So why am I doing this? You're saying, well, that was rather quick. I want to do some exam reviews prior to the statistics final exams, particularly for 151 and 161 students. And I'm going to ask you politely and with a degree of sincerity, far more than I usually do. I'm a sincere person, okay? I like cats. How can I be bad? Support us on Patreon. The intercessions are coming up, and that's not a lot of work for people like myself. I need to get some money in the bank. And we have a Tutor Wizard Patreon account. If you want to chuck a couple of bucks in there for in exchange for some online statistics exam reviews, I would say a sincere thank you for that, please. So there's going to be we'll put up a detail card at the end of the videos, especially when this ends up on YouTube, about how to find us on Patreon. I don't care. Throw a buck in, throw $2, whatever you want to do. I would appreciate it. It goes a long way to helping me pay bills. I got to buy cat food too. You know, cats are important. My wife loves cats, so I'm obligated to support her cat habit. I keep teasing her that when time finally comes around to retire, we're going to move to the southern prairies and have a cat ranch. Not the proverbial chicken ranch that people make old people reference in humor, but a little cat ranch in the middle of nowhere where all the pussies can roam free. You can say that on the internet, can I? I can say pussy on the... I'm talking about cats, by the way, on the internet these days. I hope so. I'm looking around going, they got really quiet over there as soon as I dropped the P word. What's going on? Oh, someone did. Thank you, Lorenzo. Thank you. Okay. I do appreciate that.
You want to mention the review sessions? That'll be.
Well, why don't you somebody come up here and tell me about that? Because I'm currently in stats mode. So,
Okay, well, Adrian will give a spiel when he goes
Patreon support. And you may have noticed, or notice YouTube is running thousands of ads now. I watch South Main Auto because I like to spin wrenches. I mean, I'm a Renaissance man, if you will. I can do math. I can spin wrenches. I can play with kitties. Oh, you're back. Oh, hi. I think he's horny, actually. I'm not your type. The point is, YouTube isn't paying worth anymore. I'm sorry, it just isn't. I follow Eric O on South Main Auto. Almost all of his support is done through Patreon or other channels. I follow Big Clive because I like electronics. I like to tinker with electronics. I noticed that he's gone to a whole different model. He's always had Patreon and things like that as well, but he's doing that more so. There's a couple of other Drachinafel, who does naval history. Again, all the support is all external to YouTube because YouTube pays nothing anymore. And you know, the tragedy is, I listen to CBC quite a bit, a public broadcaster here in Canada. YouTube is now the world's largest entertainment company, yet they pay nothing, especially for small people. We don't have 1 million subscribers. We got a couple thousand subscribers, and I don't know how many of those are active, but there's no money, and we're trying to pay bills here. Why do I sound like this is a telethon? So there should be a little wheel somebody in here that I can,
It's a fine line between needing stuff and just begging. Is that your coffee or mine?
That's my coffee. Get out of here. I drank it anyway. You can't have any. I'm not. I know it sounds like begging, and I suppose it is begging, but support's important. There's reasons that I'm kind of embarrassed to say that after 20-some years in academia, well,
throwing us away.
yeah. Anyway, I do have some interesting things perhaps in my near future. I'm not going to share them online just yet, but I work with special students, and we've got a research project underway, and I'm going to tell more about that in the future because I think it's indicative of how, in some aspects, particularly in STEM, science, technology, engineering, mathematics, education, there's room to do things differently. So as I get further into this research project, I'll share some details of that. I think it's a really interesting thing. Are you done eating that bread yet, or what?
Yeah.
Are you talking next, or am I?
don't give a fuck.
Or did you want to talk?
I'm going after you, yeah.
Oh, okay. So, just whoa. You want me to get rid of that? Here, I'll get rid of that. Oh, we're limbering up. See, Adrian likes to do his karate thing, and I hurt my back here, over the year. So he was doing the leg thing, and I just took my cane and went yoink. Carry a cane, and anybody gets the high stepping, you just go yoink, and that's the end of that. Okay, so Patreon support. We would appreciate it because there's we never see Lorenzo. Lorenzo, put your face up here, dude.
That's all good.
Now bring a cat then. Okay. Well, there's three
No,
of
because
us.
then I have to pixelate it. He's not allowed to have his face. We went through this.
Been like 6 years.
Okay.
Still can't show
Why
it.
don't we trade off
That's
the
another
microphone?
guitar.
Then you can have that cat over there.
I'll go grab the cat. Thank you for your attention today. I know that was a rapid fire statistics tour de force for analysis of variance, but it's something that I've always been
You don't
able to
have the
do.
microphone anymore.
Sorry. There's always something I can always do in 20 minutes, half an hour, whatever it takes. But this is indicative of what I want to do for
Getting
exam
close,
reviews.
Getting close.
If you don't hug back, it's me grabbing you. Anyways, if you thought that was rapid fire, watch this. Go away now. Or I will taunt you a second time.
All right.
Have that cat.
Big a night, or
Yeah, no, that is Monty Python and the Holy Grail. Tell them we already got one. I told them we already got one. Fetch a lavash. Fetch a lavash. What are you looking for?
Well, I was going to do the swallow thing with you, but then again, I'm talking about birds.
whoa, whoa, whoa.
Whoa, whoa, whoa. I'm the top. Always. There's a rule.
No, he's not.
All right. Before this goes off the rails.
Okay, yeah. I was supposed to be good, and the first thing I said was, I'm the top always. Fuck. All right, reining it back in. This is
Monetization.
kid friendly, and yeah, now I got a new job tutoring, and it's like I'm a good boy. Honest. Unless you're gonna do it. All right. I just have to show. So first of all, no McEwen questions while we're doing our live stream. But what Tim is saying is we need FU money before we tell everyone to FU. Is the way that what he's politely saying. I didn't do that, and now I'm suffering. So please support me on Patreon. What were we doing last time? We were doing Pythagorean triples, and then I tangented to a tangent, and then I did iterated tangents, which I'm going to continue today. And then we'll go get cat food for the very aggressive. Oh, he's being a good boy now. For the kitty sitting on Tim's lap. Plural.
Is that a lap dance?
Yes. Oh, there's a cat joke in there somewhere.
Damn right there is.
All right. So what I showed the first time was, let's reiterate, because repetition is the key to mastery. If you have, let's call it 2k plus 1 versus this is modular arithmetic, we could do a tangent, but how do you phrase this? Oh, can we do a tangent immediately? That's not how my brain works. I like to do math, and I'm doing it however I want instead of having to do it in a curriculum and PowerPoint, and you need to do exactly like this. Just purging math and talking about it for math because it's fun and I like it a lot. And I've spent a lot of years reading a lot of books about it. And if you didn't like math and you think I'm crazy, maybe that's why you didn't like it, because you don't want to compartmentalize. What you have to do is open your mind, open your mind. I was watching Rick and Morty again, where they've got the Quatos, open your mind. But it seems like I'm sporadic, and that may be true. And it seems like I have OCD, and that might be true. I'm not sure. But I define myself through my strengths, not my weaknesses. The reason it seems scattered is every time I start doing a problem, my mind is trying to open and access anything that would be useful to try and solve the problem. Because you get problems at hand, and the cliche is true. The question you ask is the most important thing, and then you have to use any kind of math that you can think of to try and solve the problem and think outside the box. This is what the mathematician is trying to do. So I immediately say that you know this as divisibility. So when we do dividing by 2, we can divide p by 2. There's only 2 choices. The remainder can be 0 or 1, which is binary. The binary or bits is binary digits. The only 2 things you can have is a remainder of 0 or a remainder of 1, because the division algorithm says that p can be 2q plus r, where r is strictly between 0 and strictly between b minus 1. So the only choices of this, if there's integers, if you look at this inequality, means that the only 2 choices are r equals 0 and r equals 1. When we do that, if in this case, if r is 0, we say that 2 evenly divides p, and it's an even number. This is where we get this, what we say evenly divides in any case. And then if it's not, it has a remainder of 1, so we call this an odd number. But what that means is, then we have this congruence definition. So just quickly, m, and we're going to use m equals 2 in this case. But what does this mean? The lingua franca back in the day was Latin. So congruence means that we want them to be similar, like congruent geometric figures. But it's not equals. We already have an equals land. What we mean is this is with measure. So we want them to be similar, in plain English, with the measure of the positive integer, m equals 2. So they're not equal to each other, but they're going to be similar to each other in the fact that all numbers either leave a remainder of 1, and they're congruent mod 1, or they're congruent to 1 mod 2, or they're even and they're congruent to 0 mod 2. So the tangent that I was doing was congruence mod m is really meaning the measure of this. So A is congruent to B mod m, we write, for any m greater than or equal to 2, if and only if, by definition, A and B leave the same remainder. And so in this case, P would be congruent to 1 mod 2 is how I would write this in congruence land. And P would be congruent to 0 mod 2. And there's only 2 choices in this scenario. Okay, tangent over. So they're either 0 or 1 mod 2 when I divide by this. Now, what I did last time was I said I can generate, so what we're looking for is all Pythagorean triples. We want all triples A, B, and then I'm going to use a semicolon C to say that we would have a right triangle. And we want that the sum of the squares of this is equal to each other. Hi, get over here. Get over here. Hi, Milo. I know you're dedicated. This is not my cat, by the way. He just comes here and tries to hump everything and eat everything, and then he leaves. Good kitty, good kitty. I know you're gonna make me trip on you. I know. Oh, good boy. So what we're saying is c squared and then a squared and b squared. This is why they call it squared. This says that the area of this square plus the area of this square is equal to the area of this square. Everything's very geometric, but they get rid of it because once Muhammad bin Musa al-Khwarizmi invents algebra, everybody wants to get rid of the geometry. Oh, the power of algebra. Bruh. We're going to do a whole series of algebra. Algebra. Bruh.
I think we should do math in monosyllabic.
So this is what I mean by a Pythagorean triple. That's the notation I'm going to use. So C is the hypotenuse. And then we're looking for all, but what that is a squared plus b squared equals c squared. Now is what we call, we're looking for integer solutions. You can look for rational ones, and I might get into that today too, but I'm going to do a tangent, then I got to go do adulting, including going to get cat food for said cat. You don't even live here, but you still got to feed them. And then that's how they keep coming back every time. So this is the triples that we're looking for. And then if we're looking for integer solutions to this equation, this is non-linear. Why is it not linear? Because we have squared in each of the terms. So this is what we call a non-linear Diophantine equation. EQN. I'm not writing it out. But if we have a non-linear Diophantine equation and we want to say solve, so in math, what we mean by that is find all solutions. I don't know why that became an I, became an O. Fond. Let's fond all the solutions. All, not some, not most, all of them in particular. And we want to know this, and this is the tangent that I was going to do. And then I'll do the difference between linear ones and nonlinear ones, but I'm going to use the Euclidean-Bozusian algorithm, so we'll do that after. Let me not tangent too far. So we want to find all A, B, C that satisfy this, that are integers, and then we'll use element of the integers. We're going to stick to positive integers also, because the real world dictates that A and B and C can't be 0, or there would be no triangle, and they can't be negative because I don't know what negative length is on the side of a triangle. So we're looking for positive solutions to this, positive integer solution to this. And that's where the Diophantine essentially means that we're getting integers. Otherwise, you could just solve this with infinitely many numbers, just pick 2 numbers. So also, I should point that out. The 2 special triangles you have are, and nobody knows the terminology anymore, that one's probably closer, that one and that one. And then if I use the root 3 and then 1 and then 2, and then I use root 2. You can always find, if you have 2 integer sides, you can always find the other side, but the other side is rarely an integer. So if you look at this, 1 squared plus root, oh, did I do that wrong?
No, that was right.
Yeah, root 3 squared is 2 squared. Oh yeah, I was thinking 2, but no, you square it. You dig down.
Spiral of Theodorus.
Yeah. I'm going to do this in a second too. Now you're going to make me tangent. How do you find all the square roots using what nature does with the golden ratio? How do you say that? The divine, say divine proportion in Italian. Say it super Italian. Divine proporzione.
Very good.
Yeah, okay, yeah, very good. That was Lorenzo's way. We're going to dub Lorenzo over me in that spot eventually. Here's me talking Italian. I'll just move my lips like the horse chewing fucking our peanut butter.
Right, Mr. Ed.
Mr. Ed. So this, and then this one says 1 squared plus 1 squared is the root 2 squared. And why are these the two special triangles? Because this is pi over 3, and this is pi over 6, and this is pi over 4, and this is pi over 4, and this is basically the unit circle encapsulated in these two triangles. But rarely do we get all integers. So we want to find all the integer solutions. Rant over, or explanation over. So now going back to this, and having said this, I want to solve the Pythagorean equation, a squared plus b squared equals c squared. And a lot of people have done this over the years because this has come down from thousands of years and through a lot of different societies. So what I showed was, I like secrets. I hear Ed Leonard's words and shut up back there. I know you're talking about related things. Ed Leonard, thank you for humbling me. I don't know everything. I'd like to say it's asymptotically tending towards this upper bound as time increases. So I want to solve this. I'm easily distracted. Kitty. And then what I'm going to point out is I can generate, so I start doing this and I give a clever method. If I square this guy, p squared will also be odd. Should we just square it and show you that it's odd? Which means you multiply by yourself because it's the two sides of the triangle. And then you can use let's just use all the distribution rules, which you should probably need to see. What I'm doing is treating this as 1 and distributing it onto both of those. So that will be 2k plus 1 times 2k plus 2k plus 1 times 1. And then I'm using the axiom in the next stage. I'm lazy, so in the next stage, multiplying 1 doesn't change anything. Then what I'm doing is I'm commuting these things. I'm allowed to turn these things around. 2k times 2k plus 1 plus 2k plus 1. Now I'm going to distribute this thing in again. I'm just using the rules of the vector space or the algebra rules that you're allowed to use. Everybody thinks, where do you get this first, outside, inside, last? I wish they would show you that this, all I'm doing is reapplying all of these rules that never change, and then you can get everything. So now I commuted those, and now I'm going to turn this into this. So that'll be 2k times 2k plus 2k plus 2k plus 1. Now I'm going to group like terms and multiply this together. This is going to be 2 squared is 4, and then I have k squared, and then I have plus 2 plus 2. Barney was right. He was right about some things. You love me, I love you, we're a happy family. These are lies from the tablecloth, but otherwise he had some stuff right. 2k plus, and then we have a 1. So I grouped the like terms together. And now what I see is, what do you mean by, if I'm showing now that if p is odd, then p squared is odd. I might have done this once, but it's okay. You're allowed to do it again. Einstein says he liked to used to do calculations that he'd already done just for the sheer joy of doing it. And to remind you, I want to see that there's 2k plus 1 in this. So there's a 2 in this and there's a 2 in this. So I'm going to write that as 2. And then I have 2k squared plus 2k plus 1. But that's my q. So it's odd because of the closure of positive integers. This is also a positive integer because multiplication and addition won't change this. So long story short, what I just showed you using the axioms of the real numbers is, or the algebra rules, is p squared is also an odd number. 2q plus 1 is my justification for this. Good. And then from that, what I cleverly notice is if I added q squared to both sides of this equation now, which actually what I'm doing is this. I'm adding 0, or what they say is what you do to one side, you can do to the other side. So we'll do this. No, plus I said. So I've added q squared to both sides, and then I cleverly noticed that this is equal to q plus 1 squared. So I have a Pythagorean triple. I'm going somewhere even slicker than this. Have you seen what I'm going to do? Remember, I'm trying to solve and find all solutions to this. Now, I can generate infinitely many for any odd number larger than 1, strictly larger than 1, because 1 will give you a quotient of 0, and then that means the side of the triangle will be 0, which is bad. We're going to do it in a second. So what that says cleverly now is if I pick p equals 3, then what do I get? Is 9, which is also odd, which is 2 times 4 plus 1. So q is 4. And I get the 3, 4, 5 triangle because 4 plus 1 is 5. Okay? Then if I pick p is equal to 5, I'm going to get p squared is 25, which gives me 2 times, now I have to do 12, good. Oh, that gives me the 5, 12 plus 1 is 13, so I get the 5, 12, 13 triangle. P equals, what's 7? No, 3, 5, 7 is Tim's favorite. That's going to give me p squared is, plus it's the only triple prime, which is double twin prime pairs, but that's going to give me 49, which is, 48, 2 times 24, oh, there it is, plus 1, that's what I wanted, so that's going to give me the 7, 24, 25 triangle, and that's as far as I need to go because I'm going to show something in a second. So let's list those. Let's list those out for us. So now, using the odd numbers, what I've done is I've shown that if p is 3, I got the triangle 3, 4, 5. If p is 5, I get the, oh no you don't, ninja, 5, 12, 13, 13 triangle. Where is that? Give me more of that. Does it taste good? Still no. Still no. Oh, that was a mistake. That was even worse. Shame on me this time. Stop eating the chalk. The glue's gone, so I got to switch to chalk. And then the 7 gave me the 7, 24, 25 triangle. So notice I went past, and the numbers are only going to grow from here. The numbers are going to get bigger from here. So think about that for a second. Now, I'm going to do the same trick. Any even number can, so I can generate infinitely many primes because, we could also prove this, but Euclid proves that we did this once, didn't we? Last time, that there's infinitely many prime numbers. So because there's infinitely many primes here, I have a way of generating infinitely many solutions to the nonlinear Diophantine equation, which is known as Pythagorean triples. With p equals 2k for any even number, I can also generate infinitely many more Pythagorean triples. So let's do that one. So this one got me more than once. It took me 3 tries, and I had to throw paper away and be like, what the hell? And then I'm reading my own notes, which I give to the Math 160, and there was a typo in there, and then it just threw me off, and I was trying to regurgitate. So this is also a life lesson. I'm just trying to lazily copy what I had already written like 5 years ago or 6 years ago. And there's a typo somewhere or something, and one of the lines doesn't make any sense, and I couldn't find it. So what did I do? I ignored it, and then I regenerated it myself. Just watch. So now p squared is going to be what? 4k squared. Oh, I tried to find it. Sorry. You don't get to hear the noise. Sorry. Oh, darn. They're like, thank Christ. I hate it when he does that. So in this one, long story short, now I'm going to call Q this guy. Why? Because I'm clever and I'm already regurgitating, but I'm trying to mimic this idea. So also, you're like, how are you doing this? I'm being a little bit more sophisticated. And last time, Q and Q plus 1 worked when I added it to the P. This time it's going to be Q minus 1. So what we're going to cleverly do is, do you see why the Q minus 1? Because I have too many Q's here. I need a 2Q, right? Oh, I'm using the right finger. But if I use Q minus 1, what am I going to get, Tim? Negative 2 plus 4 Q's is 2 Q's. So I'm going to add q minus 1 to both sides. Oh, there it was. Okay, now I know how to get it. I'll avoid it. Sorry. That's probably really annoying. If you're trigger warning by that, you're not going to last long in our chat anyways. So this is going to be p squared plus q minus 1 squared. Do I have to FOIL it out to see it? Yeah, I guess we should. We're live on the stream. This is q squared minus 2q plus 1 plus 4q. And then I combine these like terms, and I get q squared plus 2q plus 1, which is q plus 1 squared. So I get the Pythagorean triple p q minus 1, q plus 1, which will generate infinitely many. Now let's compute a few of these guys. And I also know something which has gone further, or I use from literature, so I would have read the things with Aryabhata and Brahmagupta and a bunch of these people, Heron, and a bunch of the Greeks that are doing this already, Diophantus. I should probably move this freaking TV. The chalk on it's probably not doing it any good going into all the ports. Every single port has chalk in it. Good. We'll use the spray thing. I'm easily distracted. So, P equals... Kitty, please be my prisoner. Courtney, you know who I'm talking to. You know who I'm talking to. I've still got your handcuffs. What? P squared is 4, which is 2 times 2. Is that going to work? Yes, because then what do I do? No, it won't, because it'll give me 1. So in this case, it has to be strictly larger than 2. So we're going to start with 4. Do you want to see why that didn't work? I guess that also is good. P squared gives me what? Then we're going to get, because do you see why? I saw it in my head, but then I erased it and said, no, that's not going to work. So P squared is 4, which is 2 times 2, and 2 plus 2, and 2 to the power 2. And the day I was born in February. 4 is special. All numbers are interesting. That's interesting. But now what do I take? This is my Q now. And then I have to use Q minus 1 and Q plus 1. But then that's going to give me 1. And then, did I do something wrong? Oh, I did. Do you see it? The Q is the 4 times whatever the number is. Remember when I squared it? P squared is 4K squared, which is 4Q. That's what I'm using. So I have a 1, and then Q is 1, so Q minus 1 is 0. So it will give me a length of 0 on the triangle. Also notice that was extremely good that happened in the live stream, because I'm a doctor and I'm fancy pants. Slow your fucking ego down a little bit. Frickin' ego. I make mistakes. It's better to try. This is why you think you're not a mathematician and the gatekeepers are making you stomping on your ego and making you feel bad about it. You should be trying to welcome you in, because the first rule of Math Club is please tell somebody. The second rule of Math Club is please tell somebody, because no one will join and everybody thinks you have to be fancy pants. No, math is constantly making stupid mistakes and going, oh, I made a bobo. Nobody's going to blow up. I said bobo. Nobody's gonna blow up. And do you see that? I did that 3 times and I tried, and on the 3rd time I got it. So you try it once and you're like, I guess I'm not a mathematician. No, you just keep trying until you get the calculation right and everything works. And you have to say some stupid things sometimes to get the right thing. That's persistence is key. The PhD that I have is 90% hard work, 10% fancy pants. I rarely wear pants. If you see right now, I'm Donald Duck in it. So the fancy pants has little to nothing to do with it. They're laughing in the background because they're like, yeah, he doesn't wear pants sometimes. It's like, I keep telling them, we're coming over. That's why I text, I'm on my way. Okay, so 2 doesn't work. Let's use P equals 4 as the first even one, which is not 2. That's going to give me what? Oh, numbers are going to get big now. P squared is 16, which is 4 times 4, which gives us the same triangle, which gives me Q minus, so this is the Q. Oh, Q minus 1 is 3, and Q plus 1 is 5, so we get the 3, 4, 5 triangle again. So both the even and the odd. So notice that first of all, that's good because some of the numbers are doubling up. I think I'm allergic to this chalk. I'm fighting off.
The blue chalk is friendlier.
Okay, it's Franglier.
We can go back to the whiteboard next time.
It's all right. I also, this is a life lesson. Just toughen, suck it up, Buttercup. Suck it up, Buttercup. I like the chalk. It's just I happen to be possibly allergic. I think I'm allergic to cats too, but you know what? I've got 5 of them. Toughen up, toughen up. Okay. P equals 2, 4, 6 is the next even number. He's perfect. 6 squared is 36, and then divided by 4. Tim?
9.
Yeah, there it is. 9. I said yes. So this is the Q now. Also notice with the even ones, there has to be 2 odd ones every time. Does there?
I think there's always 2 odd ones.
Well, amongst any 3.
Yeah. You can have, just a second. Okay. Q minus 1 is 8. Oh, so no, these are all even, but why? Do you see? See? They just, I don't know if you can hear them, but they both guessed you always have to. And no, I just found the 6, 8, 10 triangle. Oh, why? Because it's a multiple. It's 2 times the 3, 4, 5 triangle.
Scalar multiple. You just scalar multiple in your vector.
Yeah, and that's the theorem. That's the theorem I was going to get to probably next time. Is once you find the primitive Pythagorean triples, multiplying by a rational number or an integer gives you all other kinds, which will give you an even number. So d times the primitive Pythagorean triples would be p squared plus p squared minus q squared 2pq, p squared plus q squared, where 0 is strictly less than q is strictly less than p, are positive integers. These are the primitive ones, and then if you multiply by d any number, what we just did was use this primitive Pythagorean triple. We multiply by 2 to get the 10, 8, 10. So this is the 6, 8, 10 triangle.
Are all primitives 2 odds and an even?
Yes, because why? It has to do with the properties of when you add an odd and an even number. So if p is odd, right, p squared will be odd. If q is even, q squared will be even. But an odd plus an even always has to be odd. So the other r squared, this has to be odd also, just by the properties of the squaring all these. I'll talk about that next time then, in case you don't know what I was talking about. So then we got 6, 8, 10. So now let's talk about this with p equals 4, p equals 6, and p equals 8 should be enough, I think. Maybe I might need one more. This is going to give me, so the 4 gave me the 3, 4, 5 triangle again, which doubled up, which is okay. Doubling up the solutions, just like when you're finding solutions in the unit circle sometimes, if you reiterate the solutions, this is okay. Missing one is not okay, which is what we're about to do. The whole point of today's talk was we're going to miss one with these 2 calculations. It gives me 2 methods of finding infinitely many Pythagorean triples, but if you don't use the primitive ones, you'll miss some of them. So you don't have all the solutions, so you haven't solved the Pythagorean nonlinear Diophantine equation. 8 gave me what? This 6 gave me the 8, 6, 8, 10 triangle, which is 2 times this one. Now 8, let's go to 8, and I think it's going to go past, we need to go past 20, because the one I'm looking for is, there's a 20, 21, 29 triangle. And that's not in either of these lists. So let's check. P is 8, and I like doing the root 4s. Holy crap. Now we're going to get what? 64, which is crap. 4 times 16. Oh, okay. So then we're going to get 15 and 17, right? So 8 gave me the 15, 16, 7. Oh, is that, did I do that right? Let me double check. That pleases me that we got a consecutive. Can you find consecutive? Find another consecutive other than 3, 4, 5? No, you're right. It should be this. Yeah, I was like, what the fuck? There's a second. Yeah, this is Q. So yeah, I was like, that can't be. That would be too pleasing to me. Does that prove that? Can you prove a theorem that says the 3, 4, 5 is the only consecutive one? I don't fucking know. I don't know is a good thing to say when you're a mathematician. Also, that leads you to almost starting to figure something out. But you have to say I don't know first.
Not knowing is the first step to knowing?
Yes. And being able to say I got that wrong or I don't know in the help center is why all the full-times avoid it because they don't want to say I don't know. Let's do one more. I think it's 10. So 10 squared is 100, which is 4 times 25. I think Tim just did that calculation. So now let's not get it wrong. There it is, 24, 24, 26, right? Which is a multiple of another one. So that's the 10, 24.
Multiple of the p equals 5. Yeah.
Yeah, 26. Yeah, the 5, 12, 13 triangle. Very good. 26 letters in the alphabet. M is halfway. So do you notice that now if I do p equals 10, I was like, please be the one. I don't want to calculate these things anymore. This is where a computer comes in. You use it as a tool, not a crutch, ChatGPT. Ask ChatGPT to do this. Probably not.
Well, nowadays it can, but 2 years
It
ago,
can, but would it be able to understand what's going on? Now can it articulate? Do you see that this guy in the even ones would have to show up here somewhere, and then the odd ones would have to show up here? So if you keep going with the odd numbers, you can generate infinitely many Pythagorean triples. If you do the even algorithm that I just gave you, you can also generate sometimes distinct, sometimes doubling up Pythagorean triples, but we haven't found them all. So next time, what we'll show is we'll use a geometric argument using on the rational decomposition, which I did a little bit of. I'll give you the idea. What you do is you can pick any one of these, but in the book I stole it from, they use -1, 0, and then you think about lines through here with rational slope. And then so what that says is the equation has to be mx plus 1, and then we get to do long division. And then what do? I want the other point on here. I know this is one of the points. And then I want the other points on here that satisfy what? The unit circle. So y is m plus 1, this guy. So now I have a quadratic, and that quadratic has to have the factor x plus 1 because I know 1 is on this guy. So then the other factor will give me this guy, and then next time, think about it, do it yourself and see what we get, and we'll compare results, but then we'll use that to show, how do I know that everything's on the unit circle first? Let's do that, and then I'll leave then I'll resum this up again. First of all, you would have, how do I want to say this? A squared plus b squared equals c squared, but now divide by c squared, and you get rational points on the unit circle. That's the connection between this idea and this idea, because I can reduce the Pythagorean triples to rational points on the Pythagorean circle. Then we're going to do this thing. Then we'll find the values for the m's. It turns out to be the rational parameterization of the unit circle will be, I'm looking for points A, this point A, B. The A is going to be 1 minus m squared, 1 plus m squared, 2m, 1 plus m squared, because I've done it before, and then we'll connect that to the Pythagorean primitive Pythagorean triples.
that looks kind of like the Weierstrass substitution.
A little bit, yes. But do you notice, Mark would be proud, I drew a freaking picture and I used geometry to solve the Pythagorean identity. It was a geometry problem originally. The algebra is fun, but these things that I stole from Andy Liu don't generate them all. This will generate geometry. Draw a picture, Andy. That'll draw them all. I'll see you next time, I guess. We're ending here. They didn't know. I didn't know either, but that's where we're stopping. Try to solve this thing. Try to get this, and then from this, what you want to do is, you're like, you said you're stopping, and then you kept talking.
My finger was hovering over the stop button. But
He's like, sometimes he doesn't. So we had the ABC originally.
Full stop.
Then we had the point AB. Do you see here? Then we're going to go and solve for the C, and it turns out to be p squared minus q squared, 2pq, p squared plus q squared, specifically where they're both positive integers and q is less than p. That will generate and solve all Pythagorean triples. including all of these.